So now let's see if I can help you discover the universe for yourselves a little bit. And we'll do that by trying to answer questions like, what does the universe look like from the Earth? In case you looked up, especially in a nice summer night, you probably wondered, why is it that stars rise, kind of reach a maximum altitude or height in the sky and then set, and why is it that the constellations that we see depend on latitude, that is where we are on the surface of the Earth, and also of the time of the year. So let's start. Okay, so here's the thing. We often use the term constellation to describe patterns of stars, all right, such as you probably heard about the Big Dipper or the stars that outline Orion, which we already talked about a little bit in the previous week. We mentioned that in the previous chapter. Just as a reminder, with the naked eye, we can, if we're lucky, that is, if we're far away from stadium lights or city lights, right, we can see not much more than 2,000 stars. That is on a really good dark summer night, if you want. So really good night sky sight. As well as also in the summer, you also see that's kind of a band of light that looks like someone spilled the milk, and of course that is the Milky Way, right? So hey, that is here, this one, right? This is where the Milky Way, which is basically the galaxy within which we live. It's like you're a grain of flour in a pancake, and you see through the pancake. That's, you know, what you're going to be able to see. You look above or below the pancake, you're going to see the rest of the sky. Okay, so of course this is a really nice image, and that shows some structure, and in particular, you know, these dusty lanes. They're basically in a very center of that pancake of our own galaxy. We're going to talk about that in a whole chapter where we study our own Milky Way galaxy. Also, there is another name for this Milky Way in case you didn't know. Kalia Lactee. Right? It's the way of milk. Another way of, you probably have heard of that, so just put it out there. All right. Okay. So we said we use the term constellations to describe the patterns of stars, because they do seem to follow patterns, or they're merely our imagination that they follow patterns, right? However, technically, a constellation is a region of the sky. So a very useful analogy here would be a constellation is, for the sky, to the sky, what a state is for, say, a map of the United States, right? So that is, wherever you point on a map on the United States, you are in some state. And so very much the same, wherever you're going to point into the sky, you are going to be in some constellation. And it turns out there are 88 regions that cover the entire sky. So now here's a question. What do you think about the brightest stars in a constellation? Of course it is the brightest. There are lots of not so bright ones. There are many, just not visible to us. And they do exist in any of those regions of the sky that we call constellations. So anyway, let's talk about the brightest stars in the constellation. What is it that they all belong to the same cluster? Is it that they all lie at about the same distance from where we are, which is on the surface of this planet called Earth, or they may actually be quite far away from each other. And actually, the answer to this question is C. They are really quite far away from each other. So it actually, if you have, say, something like the Big Dipper, which kind of looks like this, right? And you have some, I don't know, the handle, I don't know exactly what those, right? So that would be the pattern, right? So we're talking about the Big Dipper, and then that's those are those stars that point to Polaris. All right. It turns out that these stars, they could be so far away from one another, actually, much further away from one another than, say, a totally different constellation, like, I don't know, Cassiopeia, which, has stars in like a W shape, which is on kind of the opposite side of the Earth. Say the Earth is here, and you're looking this way, you can see the Big Dipper, but like half a day later, you're gonna see this side because the Earth rotates around its axis, right? So it's possible that these two stars are much further apart from one another than, say, how far apart is this star from this star. Okay, so it can be very deceiving. Okay, and that is because there's this illusion that all of these things that we, most of them you call stars, and most of those things that you actually see with the naked eye are stars. There's this illusion that they're all lying at the same distance in these constellations, okay? And it's because of that illusion that we define the celestial. We define this celestial sphere. Which is actually a just an idea, right? It's not a real sphere, right? It's just a place, right? It is an apparent, right? It is an apparent spherical shape, okay? Everything appears to lie on this sphere that we make up mainly because of the fact that the Earth is round, and so everything around it will be projected on the sphere, right? And so on that projection, actually, we see stars like this that are definitely different, much different distances from each other, from us, that is from Earth, but they all appear to lie on the celestial sphere, right? So this is how the celestial sphere looks like. We have the Earth in the very center. A few words now about the celestial sphere and some of the elements that are going to be very useful, to refer to, which would define this celestial sphere. And we're going to start with the north celestial pole. Okay, so it's this one, which obviously is the point that is directly above the Earth's north pole, right? North pole here. Let's use another color. North here, south here, and so it's going to be the same idea with the south celestial pole, right, which is obviously going to be directly above the Earth's south pole. And so along the same lines of arguments, right, you have the equator of the Earth, and you project it out, and it's going to meet this celestial sphere into the celestial equator. Another very important element of this celestial, and which is going to help us understand some other very important things, is the ecliptic. Ecliptic is this path, okay, which, as this definition says, is the sun's apparent path through the celestial sphere. Now we know that the sun, right, the sun would be here at various times during the year, which is to say the sun is actually projected onto the sky in that region, all right? Because we all know the earth is the one that moves, revolves around the sun. But from, as you look at everything out there at the universe, from the surface of the earth, you would see the sun as it's projected onto the rest of the things that make up the sky. Here's another way of looking at the same thing, and maybe also helping with understanding why the sky varies as the earth orbits the sun. Okay, so we have the sun here. Sun. I don't like that green. And the earth that's moving around in its orbit, and it's going to take 365 days, or the months, 12 months, and we have here labeled some days in each month. So we have here, for example, where the earth is positioned on August 21st, right? So of course this half of the earth will, when you look up, you don't see the sun because it's below your horizon, right? And what you see is the night sky, so it's actually going to look like that, right? So that's the part of sky you would see on August 21st, right? So that's pretty much your horizon line. You can't see anything under that plane or line, right? So you look up, that's you, okay? And you look up, and that's the part of the sky that you see, okay? Straight up is going to be this part of the sky or constellation called Aquarius, right? Okay, but during that day, right, during the day, the August 21st, but the day part of the day, you look up and you see the sun, right? So of course you see the sun for half of the day, the other half, right? So that's going to be the daytime. Of course, you're not going to be able to see these parts of the sky where the Scorpius or the Libra or the Virgo or Leo or so on, right? Constellations are, because the sun is just too bright. It outshines the rest of the things that exist. They're still there. They didn't disappear, but they're still there. And look at how, because we know where things are positioned in the sky, look how the sun is actually projected in the Leo constellations. You know, that kind of makes sense now on that might explain for you how these zodiacs are put together. What might not explain to you is, for example, this situation. So you're on, I don't know, somewhere June 20th, right? So this situation, and during the night you're looking up and you see, wait, which constellation? So it's going to be Sagittarius. There is another one that's Ophiuchus. You probably didn't see that in the zodiacs, right? In the Scorpius, right? How about this? Somewhere in between November 21st and December 31st, right? So you see, during the night you see the Gemini, but during the day the sun is projected into this Ophiuchus. Well, I bet you didn't meet any Ophiuchian, or you didn't hear about that in the zodiac. So, you know, just another thought on how much you should probably trust the advice you get from those zodiacs that some of you might read. I personally love them. I think some of them are really good. It's a lot of poetry in there. But hey, in terms of actually guiding your life, I would stay away from that. But again, ultimately, it's your call on whether and what you want to do with your life. But this is, I think, a pretty good proof that, you know, what those zodiacs say about or predict about what can happen to you because it's written in the star, that could be quite far away from the reality. So here's another way of looking at the sky, right? Then we already touched on that when I mentioned that everywhere on the surface of the earth, so this is the earth, right? North Pole, South Pole, equator. You're probably here somewhere in the Shenandoah Valley, the parallel 40 something degrees, right? You know about these parallels, right? And then you know the meridians that give you the longitude. So anyway, somewhere here, this is going to be your horizon, right? So you're looking up, so that's you again, okay? And you're looking up, and guess what you're going to see? The highest point above, or well, the direction that is straight up, that's called zenith, okay? And then once you identify something in your sky, that's going to be, here, that's your cupola, that's your local sky, right? You identify an object like this one, you say, oh, I can actually quantify, measure that exact location, okay? And I can say just how far high in the sky that is, right? And I can measure that angle, right? You look up above the horizon, so this is the horizon, that is the plane you are sitting on, okay? Because you can't see anything. You can only see above the horizon, okay? That half of the universe is not visible for you. So you can see, okay, that object is at altitude of 60 degrees in this situation. And also you say, okay, I have a direction along the horizon starting from any cardinal point, and you're going to say, okay, I have a direction that is southeast, right? So let's try another one. Say there is an object maybe here that's on this meridian, right? So this is the object, or maybe the cluster of stars, right? That you want to point at, and you're going to be like, oh, I'm going to point to that, okay? So I'm going to measure the altitude, okay? That could be something like 47 degrees. You can measure that, maybe, okay? And the direction, right? So that's going to be the altitude. And then the direction, you see it here. It's very close to west, so I don't know, west southwest or something like that. So southwest, but closer to the west, right? Okay, so that's another way of quantifying these things. They're very useful reference points as well. Another thing that I want to point out, and obviously it's very useful when we want to measure things, is already noticed that we measure how big or how high above the horizon these things are. We measure them by angles. For example, if you look at the moon, you can measure the angle that subtends the diameter of the moon. That is 1/2 of a degree, right? So you already are hopefully familiar with this angle, that is 90 degrees, right? Half of it, that is 45 degrees, right? And so you keep going, that would be 180, and the whole thing is 360 degrees, right? Okay. Same thing here. for the two stars, for example, that point towards Polaris, right? That's somewhere there. Okay, those two stars are separated, if you want, right, by an angle of 5 degrees. Okay, just also for reference, so we have here another reference point. Okay, if you stretch out your arm, what you should be able to measure, like the thickness of one finger, any one, it's around 1 degree. Okay, and your fist, that measures an angle, right? So basically, if this is your eye, okay, that sees your fist as subtending 10 degrees. Okay, and here on the bottom, there are, just for you, some definitions of what the zenith is, the horizon, and the meridian line. And you can always come back to this slide if you need to review these definitions. All right, so we do measure the sky using angles. It turns out that some things are going to be so far away, right? So say, I don't know, yeah, let's see, Saturn with its beautiful rings, right? So we're just so far away. Lost it for a little bit here, right? That, you know, say we're here somewhere, that angle is just going to be so small. So that is just one example. It could be a whole galaxy that is just so far away, right? So maybe this is us. We're looking. That's just one way of drawing the eye. You're looking. This angle is going to be so small that we are going to need not just degrees, but we're going to need to split the degrees into 60 arc minutes. Okay, and the symbol for the arc minute is a comma. Now, 1 arc minute can also be split into 60 arc seconds, and the symbol for the arc seconds is going to be 2 commas. All right, okay, so now here's a question. If the angular size, that is the angle that is subtended by your finger width at arm's length is about 1 degree, then how many arc seconds is this? Okay, so you're going to have a few exercises on Mastering Astronomy that help you go back and forth between degrees, arc minutes, arc seconds. All right, so we have 1 degree is going to be 60 arc minutes, but each arc minute, right, has 60 arc seconds, and so the total arc seconds is going to be 3600 for 1 degree. Okay. Another example would be, hey, what if something, I don't know, a cluster, another galaxy is as big as 36 arc minutes and 2 arc seconds. How many degrees is it? This is just, I'm making it up, right? How are you going to go back from arc minutes and arc seconds into degrees? So here's what you do, right? If you have 1 arc minute, that's going to be 1 degree divided by 60. 1 arc second, it's obviously 1 arc minute divided by 60, or also 1 degree divided by 3600. So here's what we're gonna do here. So what do you have? You need to convert all of these things into degrees. So you have 36 divided, which is arc minutes, divided by 60 to get 2 degrees, and then you're gonna need to add those 2 arc seconds, right? So you need to divide by 3600 to convert it into degrees, right? So you do all these calculations and you get that whole number in degrees. All right, so let me know if you have any trouble with these kind of calculations. Another useful thing to discuss the angular size, so that angle that is obtained by either the distance between two stars or two things in the sky, or the size, say, of the rings of Saturn, and the physical size, like the exact length of that distance, right? So that's a length or a side or something, right? And so we have this beautiful formula, okay? And I wanted to draw your attention to the fact that this distance and the length, you need to match the units. So, for example, distance could be in light years, and the length, right, you might need to calculate it, or it's given to you in kilometers. Then what you need to do before you plug into any stage of this formula, you need to convert to kilometers, right, to match the units you have for the length. Also, the angular size, it better be in degrees, right, which are these ones. If you get really small number, a tiny number, a degree, and maybe the Mastering Astronomy might ask you to provide the answer in arc minutes or arc seconds, you're gonna have to do the conversion, just go back and forth in between them, right? So just definitely make sure you match the units for this thing. So the distance and the physical size, they need to have the same distance. All right, so here's what happens here, right? So this is what we're talking about, right? So this is the physical size, right? It's just how tall that object is, or how wide, or right, how right? So you put the same object now further away, right? So you're gonna talk about here distance 1, but you put it further away. Distance 2, it's greater than distance 1, so further away. What happened, right? Look at that angle. So the angle used to be this, angle 1, the angular size 1, right? Theta 1, and then later on this object, right, which is the same, so same physical size, but because we have a larger distance, right, it's further away, look what happened to the angular size. That angular size is now theta 2 is smaller than theta 1. And actually it goes pretty linearly, like if you have the further distance is twice the previous distance, then that angular size is going to be half of the angular size corresponding to the smaller distance. So they obviously go in the opposite direction, but they go by the same factor. All right, so you learned a lot, but you still didn't get any information maybe yet about why do the stars rise and set. Okay, so now it seems easy to explain if you're looking at the celestial sphere from the outside, right? So here we have the Earth, and it's rotating around its axis that goes south, north, and this is going to be north celestial pole and south celestial pole, and you have all kinds of stars and patterns on the celestial sphere, right? And what do you think is going to happen, right? Because the Earth rotates from west to east, the stars will appear to us, right? To us from Earth to circle from east to west. It's really, that's all there is to it, right? Okay, it's because of the rotation of the Earth, the spinning of the Earth around its axis. All right? Okay, so now of course it's going to depend what you see and what things are circling what. It's going to depend on where on the surface of the Earth you are. Okay, for example, stars near the North Celestial Pole, they're also called circumpolar, and they are always going to be above the horizon. Like look at this one, right? They're always going to be above the horizon. Say if this is your horizon. Oh, it's here, right? It's that plane. That's your horizon, okay? That's where you're basically sitting. So you see everything above, right? So it's visible, not visible. You just can't see under the horizon. Okay, so because these circumpolar stars near the celestial pole, they're never going to be under the horizon. That means they never rise or set. Look at this star, for example, this track of this star, right? So it goes above the horizon, just here. It's going to reach its highest point, its zenith, and then, right, and it's all thanks to the rotation. That's during 1 day of rotation of the Earth around its axis, and it's going to go under the horizon. That means is setting. Also, take a look at some stars here, very close to the South Celestial Pole. Well, they will never rise and obviously never set also, right? Okay, so of course, again, that depends on where exactly you are on the surface of the Earth, right? So, for example, say you meet this question in homework or maybe exam, and you have this beautiful picture, a long exposure picture of the Arches, I think it is, in Utah. And it's long exposure because what we see here, these white arches, those are basically the location of the stars for the duration of a few hours, right? And so because of those tracks, we're actually able to tell what that white arrow is pointing to in this photo. So we have the options of that point being the zenith or the North Celestial Pole or the celestial equator. So if you remember from the previous discussion, it is that North Celestial Pole, and it is north because Utah is still on the northern hemisphere, so you wouldn't be able to see the southern celestial pole, right? That is the North Celestial Pole because the stars, you see these stars, they are circumpolar and they never set or rise, right? So this is how you figure out the answer to this question. All right. Yeah, there are ways of finding the North and the South Celestial Pole, and actually they're very useful, just in case you're abducted by some aliens and, they do whatever they need to do with you, their experiments, or and at some point they realize, hey, you might be more useful for this universe by living back on the surface of the Earth, but they're not very careful and they don't put you back on the surface of the Earth at the same location they took you from. So, hey, it would be very useful for you to actually find that location, and just in case you want to call back your parents or your friends, say, hey, can you come pick me up, right? So you need to tell them where you are. Of course, assuming that your phone for some reason doesn't have an app to tell you exactly your coordinates, right? So in that case, you're gonna need to be able to find that Polaris. So here's what you're gonna do. You're gonna look for the Big Dipper or the Little Dipper constellation. The Little Dipper is not as bright, but it's, you know, it's visible. And so you look for either, you know, the point. So that Polaris is actually one of the Little Dipper stars, and you see that rotating, you know, during the hours of the night, or you see these pointer stars we actually talked about before for the Big Dipper, right? You see how they rotate during the night, and just for the duration of a few hours they do point again to Polaris. If you happen to be somewhere in the southern hemisphere, you're going to have to identify the southern cross, is this one, and you need to look at where that cross is pointing at on the course of a few hours, right? So that's going to kind of trace an arc of a circle, and you need to find the center of that circle. That's going to be the south celestial pole. But here's another very interesting thing that you're going to be able to tell once you identify the Polaris or the southern celestial pole. So you're going to say, oh, okay, if I find out basically how high above the horizons, basically identify that angle, how high above the horizon that Polaris is, that is going to tell me my latitude, because some little geometry, we're not going to go into that. That's exactly how that angle is defined, how your latitude is actually going to be defined. So of course, if you do this thing, right, so you measure, you know, the angle, right, so that's your horizon, that's going to be the theta to south celestial pole, or right, the southern, there is no star there to actually identify, so you would need to maybe, I don't know, draw some things on a piece of paper to identify that, or just, you know, estimate, right? So you can find that, of course, that's going to be, oh, that's my latitude, so that's latitude, but that's in a southern hemisphere, right? So the southern latitude, and that's going to be north celestial pole, that's going to be the northern latitude. Very useful, isn't it? So for example, now you would be able to answer questions like this. All right, so say you're somewhere on the surface of the earth and you do identify Polaris, which is the North Star, and you measure that angle above the horizon to be 50 degrees, and that's due north. Okay, can you tell exactly where you are? Well, of course, you're not going to be on the equator, you're not going to be on the North Pole, and you don't have much information about your longitude. Okay, so these are not going to work as good answers. What you find is that you are at a latitude of 50 degrees north. Just that simple. All right. So the sky varies with latitude. Basically, it varies with where you are above or below the equator. Okay, but it's not going to matter where you are, whether say you are on the Shenandoah Valley or in China, even though they are 12 hours apart, right? So say this is Shenandoah Valley, say JMU, and here is China. And guess what? You're gonna see the exact same pattern of stars. Okay, it's just gonna be 12 hours apart, right? Because this whole Earth turns around, and just 12 hours later, you're gonna see above the Shenandoah Valley what you've seen 12 hours before in China. Okay, what matters is actually where relative to the equator you are. So say, for example, you're here somewhere in Southern Africa, right, or Australia, for what I care, it's going to be the same, because the sky is not going to depend on the longitude, okay? So somewhere from the northern hemisphere, you just draw that horizon and you look up. You're gonna find the highest point up, that's the zenith, and you're going to identify, basically you look up and you identify the position of the south celestial pole, and that turns out to be 34 degrees altitude, okay? That means your altitude due south, of course, because you identified here the south celestial pole, right, it's going to be again that 34 degrees. So you can do that with any position, any altitude, either north or south, and you will see that that matches the altitude of either the north or the south celestial pole. All right, so that's about it. You should be able to navigate your sky from now on. If you have questions, you should let me know.